Continue for okay. Thank you, Del and Professor Antonio, for inviting me for this webinar. And thank you everyone for joining this webinar. I can see around 90 people here. So today I'm going to talk about the work which we have done at University of Bristol at the National Wind Tunnel Facility, where we worked on electric ducted fan, specifically the Bondelier ingested ducted fan. And we studied the aeroacoustics in that. Before jumping into the main content, I would love to give a brief overview of myself. I'm currently working at Dyson as a senior research engineer. Before that, I worked at University of Bristol as a senior research associate for approximately 1.5 years, especially focusing on urban air mobility vehicles. I did my PhD in mechanical engineering from UCL, funded by EPSRC and British Petroleum. I came from India, where I did my master's and bachelor's degree, both in aerospace engineering. With regards to my technical interest, I am very much into the source of aeroacoustics and try to understand aeroacoustics from fluid mechanics perspective. I have worked in a wide range of area, ranging from turbomachinery aeroacoustics to duct acoustics. My main aim is to bridge the gap between theory and practice by conducting research on complex engineering flow systems. So far, I have addressed critical issues in industry, especially in terms of development of analytical and numerical capabilities and wind tunnel test capabilities, especially in wind tunnel with anechoic chamber. Now let's jump into the technical aspect of this presentation. I'm going to take you through the background of the project, the methodology which we used at University of Bristol, which is purely experimental, and then I'll take you through some interesting results and some critical discussions on that. Followed by that, I'll conclude the presentation with some future work which is being done at University of Bristol. So if you look at ducted propulsion system, there has been renewed interest in ducted propulsion system, specifically in the aerospace sector. And the reason was due to the advancement in the powerful electronic motors. And many aerospace companies have been incorporating ducted propulsion systems in their vehicle. For example, hybrid air vehicle, Airbus E-Fan, Bell X-22A, and the latest one is Green Jet. You can clearly see that the way they mount ducted fan is different in different aircraft. So generally, we can divide the mounting of ducted fan in two types. One is isolated, where the ducted fan is placed far away from the body, and which is also called as podded configuration. And another one is installed configuration, which is also called as embedded configuration, where the ducted fan is partially embedded into the system or placed just next to the airframe. If you look at the novel aircraft, future generation aircraft, they typically incorporate installed configuration. And the example here I'm showing is about embedded ducted fan. You can see on the left side, on Air Nova, the ducted fan is embedded at the empennage in the rear fuselage section. And the Lilium jet, you can see that it is embedded on the wing. On the right-hand side, you can clearly see that the purpose of using embedded ducted fan, the boundary layer which develops along the fuselage, it ingests into the ducted fan, it interacts with various components, for example, rotor or fan, and then stator, and it releases through the exit. The reason for using this in future generation aircraft is their potential for fuel saving benefits. However, there are some challenges when we talk about noise, because it depends on the design and of course the inlet distorted flow which is coming and ingested onto the airframe. And this is what, so on the screen you can see that why this ducted fan is complex in terms of noise radiation. And you can see the various sources. I have made a schematic of that, particularly from the point of BLI ducted fan. So one of the main noise is, of course, from the fan. Then we have tip vortices from the fan, which can interact with duct boundary layer, another source. And the wake of fan can interact with the stator or strut, which is the stationary part, and they can generate additional noise. Another noise we can get is from the duct itself, because duct carries some internal acoustics field in it, and it can be one of the source of that. And from BLI point of view, we have an airframe, and airframe has a boundary layer. Once the airframe moves towards the curve region, which is what we have seen in on-air configuration, we get adverse pressure gradient where there is a growth of boundary layer, and hence we have highly three-dimensional, large-scale stretch vortices, and that is another source when it interacts with the ducted fan. So this is what we have tackled at University of Bristol, trying to make the complex phenomena simple by conducting a test in the National Aeroacoustics Wind Tunnel Facility. On the screen, you can see an anechoic test chamber at University of Bristol. The black color board is S-plate, and this is the wind tunnel open jet nozzle. On the yellow arc, where we installed microphones, far-field microphones, to capture far-field noise radiation. And on the right-hand side, you can see the test setup during operational condition. And the woolen tufts are there to visualize the flow distortion which happens within the concave region just before the ducted fan. And that was the purpose of the project. So this is the simple schematic of the ducted fan, which you have just seen. You can clearly see that the ducted fan was placed from the nozzle exit around 0.8 meter, and microphones are placed at 1.75 meter. On the right-hand side, you can see the test rig was highly instrumented, especially the S-plate. Along the center line, we put pressure taps to capture flow characteristics. At the same time, we conducted a high-resolution hot wire analysis to study velocity field distribution as well. The reason we put ducted fan at around 0.8 meter is, I'm going to explain in the next slide. So the first figure on the right-hand side, it shows the pressure taps installed at the center of the S-plate. And this is, you can see the flow visualization using woolen tuff. And on top of that, I have plotted mean pressure distribution. And you can clearly see that when you move from left to right, when you move from 0 to 0.8, initially you see a decrease in pressure where we have favorable pressure. And once it enters into the concave region, where we start getting a sharp rise in pressure, which dictates the adverse pressure gradient. And hence we get a highly three-dimensional distorted or stretched vortices. And this is the reason we placed ducted fan at 0.8, because this is where we have the maximum adverse pressure gradient. And the rest of the region is just a pressure recovery region. We also did a hot wire analysis without ducted fan, only on S-plate. The ducted fan which I showed here, it is just for illustration purpose. But this is done only for S-plate, and you can clearly see that we have this negative region where we have boundary layer growth. And this ducted fan is immersed into that ducted fan. And you can see around 70 mm of the propeller fan tip is immersed into it. And we studied noise mechanism in it. So the test matrix, we use a very simple strategy. The purpose was to understand the fundamental physics. So the method we use is source decomposition approach physically. How? I dissect the overall test rig into 4 parts. First part, you can see isolated duct and the flow from the nozzle exit is released on that, and we studied noise because of isolated duct. Then we put the fan, and that's called isolated ducted fan, and we studied the combination of fan and duct noise. Similarly, we put the same configuration on the S plate just to see how the particular noise is interacting with the incoming turbulent flow and how it influences the far field noise radiation. So all these test conditions are run at a wide range of actual inflow velocities from 8 meter per second to 32 meter per second. And we did for 3 different RPMs, 6,000, 8,000, and 11,000. But in this particular presentation, I'm going to show result only for 6,000 RPM. So let's have a look at the result. First thing, of course, is the fan aerodynamic loading. On the screen, you can see left-hand side is the aerodynamic efficiency of the fan. We have 3-bladed fan, and it gives efficiency, the black line, dotted, and solid line, the typical propeller characteristics with respect to advance ratio. And on the right-hand side, you can see thrust coefficient and thrust drops when you increase advance ratio, and advance ratio is linked with axial inflow velocity. So why there's a decrease? Because when you increase advance ratio due to increase in velocity, each blade experiences reduced effective angle of attack, and hence we get less thrust. The reason, if you see the comparison between solid and dotted line, which is solid is for installed ducted fan and the dotted is for isolated, you can see that installed configuration shows significant thrust as compared to the isolated. Why? Because in isolated case, there is no velocity gradient. The inflow is uniform in nature, and we get this typical dotted characteristics. But when we have installed ducted fan, in our particular case, when we have adverse pressure gradient, we get boundary layer growth, and we have velocity gradient, and hence we get reduced average velocity, and even the reduced local velocity at each blade sections. So what it does, since average velocity is decreased, therefore effective angle of attack is also decreased. And when effective angle of attack is decreased, of course, the thrust is relatively larger than the isolated case. So this was the reason. So, but I also use the thrust regime diagram to divide my study into 2 parts. High thrust regime, and see how the far field characteristics is different than the low thrust regime. So this you can see in the next slides. Before that, before jumping into the BLI ducted fan, let's have a look at duct aeroacoustics, the comparison between isolated and installed case. In the isolated case, what we found is the noise which we are getting, is the combination of internal flow and the external flow. So we have a certain thickness at the trailing edge, and that trailing edge is causing vortex shedding, and that vortex shedding excites duct acoustics. So we have 2 types of duct acoustics typically. One is planar wave, which is below the cutoff frequency. In our case, the cutoff frequency of the particular duct was 780 Hertz. So whatever duct noise you see is dominated by plane acoustic waves. But we still have non-planar waves, which is significantly lower than the planar wave. But this you can see after the cutoff frequencies. So what I can say here is our duct noise is dominated by planar acoustic waves in the far field. But when we have the installed configuration, when there is an interaction of distorted flow in the upstream with the duct acoustic field, we see an interesting observation. We see a spectral broadening in the noise signature of duct. Plus, we get spectral humps, which is more clear in the line plot, which I can show you later. But yeah, we get spectral humps as well. This is similar to what we get in fan aeroacoustics. We have hair stacking phenomenon, and hair stacking means, which it's better if I show this plot for hair stacking. So yeah, the next result I'm showing for ducted fan aeroacoustics. Again, the comparison between isolated ducted fan without S plate and installed ducted fan with S plate. You can clearly see that it's a combination of duct noise, the feature which we have absorbed on the top plot, along with typical fan aeroacoustics, blade passing frequencies, and other broadband component. Yeah, I have highlighted only these two here. And I told you that the typical hair fan or popular hair stacking phenomenon is the phenomenon when the ingested stretched turbulent vertical structure is chopped off by popular blades is called hair stacking. So there are two consequences of hair stacking. One, we get spectral broadening. If you look at especially at blade passing frequency, it's more broadened as compared to the isolated case. So that's spectral broadening. At the same time, we get spectral hump. Again, I'll show you in the next slide. So yeah, you can see two similar characteristics, but two different names in both isolated and installed. So let's jump to next slide, which shows the evolution of the interaction between duct acoustics and duct acoustics and incoming in turbulent flow, and installed ducted fan and incoming ducted flow. On the top, you can see how duct acoustic changes with respect to velocity. Why? Because it is Strouhal number dependent as it is related to vortex shedding. It keeps on changing with respect to velocity. And in the bottom figure, you can see that it changes, the duct moves towards 2 times FBPF, and it merged with that, and it completely alters the hair stacking phenomenon, which we typically see in popular aeroacoustics. So to get more clear picture of what we have talked about, I think this is a nice figure. Just to distinguish what's happening in high thrust and low thrust. Let's have a look at high thrust regime, where, so I have shown everything here. Yellow is isolated duct, green is installed duct. You can clearly see that in high thrust regime, duct acoustic effect is negligible. So whatever we get, which is the blue color, is nothing but a fan aeroacoustics, close to fan aeroacoustics. But when we have a BLI configuration or install configuration, we get enhanced the maroon color spectra, which has two features. One is spectral broadening, and we have this humps, so which is the definition of hair stacking. Now have a look at another thrust regime, which is the low thrust regime, where the velocity is high, and of course the shedding effect is dominant, and we see that duct effect in both isolated and installed configurations are significantly high, and it highly alters the noise signature of our ducted fan, which is the maroon color. So yeah, so what I have concluded from here is the spectral broadening and spectral humps, which we are seeing in low thrust regime, is because of the combined effect of duct acoustics and fan hair stacking. Whereas in high thrust regime, it is purely due to fan hair stacking, which means interaction between incoming turbulent flow and fan loading. So I also tried to understand the concept of spectral broadening and spectral humps from hydrodynamic flow point of view. So what I am showing on the screen on the left-hand side is mean pressure distribution based on pressure types. And the middle figure is for S plate only without ducted fan. You can clearly see that, yeah, initially between 0 to 0.5, we have favorable pressure gradient, and suddenly there's a huge pressure rise where we have adverse pressure gradient. But when the ducted fan is operating in the installed configuration, this behavior is changed. And what we have seen is, we have seen a sharp transition from positive pressure to negative pressure, and we get this intense negative pressure in the high thrust regime between advance ratio of 0.3 and 0.6. You can see this negative pressure region, and which is ingesting into the ducted fan. So to get another perspective of this negative pressure zone, I did a detailed hot wire analysis. Again, trying to characterize high thrust and low thrust. So first figure you see on the right-hand side is RMS velocity based on hot wire. And you can see, if you focus on the top part of ducted fan, you see this suction effect, and which is because of, upstream suction effect because of the rotating blades. But when this upstream suction effect interferes with the adverse pressure boundary layer, we get this strong suction effect. And this is still under investigation. So this is my theory so far. What I understood here is this suction effect causes intense chopping of turbulent stretch vortices by the rotating blade. And hence we get spectral widening and spectral humps into the noise signature. But when we have a look at low thrust regime, what I observed is that incoming turbulent flow, it just ingested into the ducted fan without undergoing significant intense chopping, which we have seen in the high thrust. And this is the reason the fan, this is the reason if you look in the back, it's highly fan, the typical propeller has taken. And yeah, so to clearly understand that this suction effect comes from ducted fan, I plotted this in a line plot. So it shows the evolution along the S plate. In the upstream region, you see the figure here. I've installed, maroon is installed ducted fan, isolated ducted fan, installed duct, and S plate. Everything merged here. And the blue color, if you see, since blue color is isolated ducted fan, there is no boundary layer. That's why you see this finite value here, and everything collapse. But when you move into the adverse pressure gradient, and this middle figure is just before the adverse pressure gradient, you start to see variation in the different configurations. But when you go exactly at 0.8 meter distance where we install the ducted fan, you see this interesting behavior. Let's have a look at blue color. And blue color shows the suction effect for us. So in the hub region, we have stagnation region. But when you go at the tip, you see between hub and tip, you have this strong suction effect, which is reflected in our maroon color. And maroon color is our installed ducted fan. So maroon color has additional effect as well, which is because of the S plate, the green color. So in short, I can say that, installed ducted fan has two features. One is boundary layer growth from the wall, and at the same time, the suction effect because of the isolated ducted fan. And this was the reason we saw this flow behavior here. Yeah, so this was it about what we have done at University of Bristol. So in short, what we found is ducted fan BLI noise is the complex interaction. It's due to the complex interaction between duct blade loading in terms of blade passing frequencies and haystaking phenomenon. So we observe two different phenomenon in two different regimes. In low thrust regime, the noise is driven by fan loading and duct acoustics coupled with haystaking phenomena. In high thrust regime, since the velocity is less, duct acoustics effect is less, and it is quasi similar to the haystaking phenomena we see in open propeller. So the conclusion we can make out of it is duct alters fan haystaking phenomenon as a result of intense suction effect just upstream of the ducted fan. So based on this work which we have done at Bristol, the team at University of Bristol is still working on lots of other ideas, and the few are listed here. So they are trying to understand how the interaction between rotating fan and the stator influences the noise signature. That's one of the projects they are doing. The test rig is ready. And they're also trying to reduce the noise level in ducted fan from two perspectives. One is from blade perspective by doing some acoustic treatment, and from duct perspective by designing some acoustic silencers. Thank you, and I would love to acknowledge EU Horizon for sponsoring this project, and NOD's, University of Bristol, and ONERA for a nice collaboration. And thank you. If you have any question, I would be happy to answer.